Hello and welcome to this new video where I'm going to very shortly introduce a paper which I hope maybe will compel you to read more on the subject in the future. So the paper I wanted to talk about has to do with the so-called ER equals EPR conjecture. Um, and this conjecture basically says the following. What they mean by ER essentially is for Einstein-Rosen, and that's related to the notion of the Einstein-Rosen bridges in basically general relativity, whereby Einstein and Rosen wrote a paper talking about a sort of bridge that actually could exist between a black hole and another black hole, basically. So these basically now we call like a wormhole, then there are white holes, etc. But the bottom line here is it's a sort of bridge between two black holes. And so that's the first aspect of it. And then the EPR part of the equation relates to the Einstein-Podolsky-Rosenberg um, basically paradox. And then in that case, basically let me just check 2 seconds that I'm not butchering the words. No, so it's apologies. It's Einstein, Podolsky, Rosen, and then no, actually, sorry, it's also Einstein and Rosen bridge. So it's the same Rosen in both cases. For some reason, I thought it was different. Nevertheless, so the bottom line is basically this is discussing these two things. So one is a phenomenon within uh, general relativity, which has to do with black holes and communication between black holes, and the other one is an allegedly or apparently completely different subject, which is about entanglement in quantum mechanics. And the idea of the ER equal EPR conjecture, uh, I think if I want to phrase it um, as I kind of understand it, is basically something along the lines of when we say in thermodynamics, for example, that heat is work, heat's equal work, or something like this. So essentially, there's this idea that there is a sort of equivalence between the two, and kind of interchangeability between the two. And depending on the papers you look at, I think most of the time this is quite complicated to understand. Um, Authors are going to look a lot at string theory, general relativity, and stuff like that, and that looks quite daunting. Now, the reason why I talk about this paper by Susskind, which is on Copenhagen versus Everett, teleportation and ER equals EPR, is because I think this is one of the most pedagogical entry, let's say, to the topic. This in fact is part of a lecture series he gave um, in 2016, and I think that explains why it's like the presentation is rather pedagogical. Now there are 38 pages, so I'm not going at all to read through all of them. Just trying to motivate, in case you would be interested, to motivate you to read further. Um, so the point here is that there are plenty of qualities to quantum mechanics that make it baffling, and so that's what he discusses at the very beginning. Um, but then the point here is basically to realize what the ER equal EPR principle can actually tell us about the interpretations of quantum mechanics, and basically that's kind of the idea. So for example, so there are multiple ways of view it, but the point is to say, well, that you can exchange information in a sort of entangled fashion that you can do with quantum mechanics by preparing some systems in a certain way, by having interacting systems and so on. You can get entanglement in that fashion. But then, from a classical perspective, you can also entangle kind of information via Einstein-Rosen bridges, and basically, as far as information theory or quantum information theory is concerned, there wouldn't be any distinction between the two outcomes, if you will. And so there is this idea really that at least there's a strong equivalence or analogy between the two notions. But even more, maybe we can learn from one to understand better the other. And I think here this is what Susskind is trying to do, to perhaps interpret the Everett. So Everett interpretation of quantum mechanics is a so-called many-world interpretation, as opposed to the Copenhagen interpretation, and then try to go from there. So here he goes on to the meaning of ER equal EPR, and in particular with the fact that, from very far away at least, quantum mechanics is non-local, and then general relativity via Einstein-Rosen bridges is also non-local. And so at this very kind of basic level and like surface level of telling things, then maybe they've got something to say to each other. So here, this is just an example on how you get non-local connectivity in an EPR entanglement. So that's the idea. So two people exchanging information in that fashion, clearly being non-local in the sense of Einstein. So essentially, you would go much faster than light would take to actually do the trip, on the without the bridge, let's say. And basically that's it. So that's what is explained. Of course, this is what you can get. So in that case here, that was an EPR entanglement, while here this is an Einstein-Rosen bridge that allows for exactly the same thing to occur in terms of non-local connectivity. And so here, this is an example of the kind of things that can form entanglements in some kind of generic kind of sense. So ground state or vacuum entanglement, entangled particles, Einstein-Rosen bridges, and then of course there are plenty of other things. So here this is part of the example that are illustrating these things. So Alice and Bob that are going to talk to each other, and essentially you could do the same by using an Einstein-Rosen bridge. But the thing I would like to focus on, so first he actually kind of delineates the distinction between Copenhagen and the Everettian interpretation. So in case you're not up to date or you're not too fresh on this, then I think that's a good idea. He's basically using mostly words. There is hardly any equations. So I think that's quite useful. So for example, here he actually states, maybe I can try to increase, that the Copenhagen interpretation basically tells you that you live only in one world, okay? And the green branches correspond to what the world could have been, okay, but what the world isn't, basically. And so you've got this kind of collapse where things do happen in the world, in the universe, and things that could have happened simply don't happen, and that's it. Now, in the Everettian relative state, as it happens, actually, every event that is on your in your wave function actually happens. And then the only thing you do, that's why it's called Everett relative state, is that you try to check relative to yourself, what branch are you actually experiencing? So it's basically, if you look at a tree and then you say that this tree has only a single branch because that's the one I don't know, you're latching on or something, and you try to ignore that there are hundreds and hundreds of other branches, on there. So here it's a little bit like this. It's more recognizing that we are in a world that is kind of attached to our experience, but basically there are plenty of other worlds out there that exist. So one of the ways he actually gets into this is by presenting a very famous problem, which is called Venus friend experiment, and it has to do with basically, well, Venus friend, observing a cat, then Wigner, and then Einstein. So you need to have multiple parties involved, and each party that is outside of, let's say, one system considers a system they're looking at as a single quantum system. And I really recommend that you look into this because it leads to tons of different paradoxes, including one, although I think it has been kind of challenged recently, but there is one paradox where you essentially you would reach a contradictory kind of conclusion um, if basically both Wigner's friend and Wigner, for example, actually assume or use quantum mechanics, they would actually disagree on statements they are going to make, on what they observe. That's a very famous thought experiment. So the point here is that this is analyzed on both the how to call that the Everett and Copenhagen interpretation. So it talks about qubits, but just think of it as like some sort of yeah a bit of thing that can take 0 or 1 values, and that's enough. There's nothing kind of crazy about this, apart from the fact that you can put them in entangled states, and then tries to explain two things. What you can gain from the ER equal EPR thing, and also what then the Everett interpretation has to say about it. So you see that's how this would be interpreted in the sense of um, the Venus friend that kind of creates a sort of communication channel via an Einstein-Rosen bridge. Um, and I suspect this is the map in space-time. This would be a sort of uh, network of connections between the qubits of the cat and the Venus friend that eventually becomes meshed kind of together, and essentially they can't be like, that's what this kind of fabric-like looking thing is supposed to represent. Um, and in the end, I think what is important, as I will stop here, is that basically you can, when you have a third person coming in, where is it? Yeah, so they imagine a sort of three branch kind of ERB, so Einstein-Rosen bridge. Um, and then the point that is interesting here is that you can try to put the three-party system into what is called a GHZ state. So GHZ simply stands for the authors of this kind of notion, which is Greenberger, Horn, and Zellinger. And this kind of state is used heavily in quantum information. And the goal is simply to have a kind of state that you would put three parties into, so it's a quantum state, such that if you somehow forget about one of the parties and simply look at the statistics of the two remaining parties, then they are going to be disentangled. Okay, and so the whole point here is that you've got, if you take any, again, if you take any two parties and you look at them having so-called traced over the third one, so as if they didn't exist, in a sense, then you would get that the two parties are not entangled. But then if you look at the from the point of view of the three together, then they are entangled. So it's a very typical kind of state, but that lead people to get different conclusions about the entanglement state of the system. So that's what is explained here. So, I mean, that's kind of the idea. So there are come like very relatively simple diagrams that kind of everybody can try to understand at least, and connections to kind of black holes. Um, so, so that's the idea. There is also so-called strong and weak version of the ER equals EPR conjecture. So the strong kind of ambitious version consists in saying that all quantum phenomena, include, in particular those that involve entanglement, have to do with a sort of quantum Einstein-Rosen bridges that are connecting quantum black holes. Um, but that's not necessarily what this conjecture says. It says that you could basically reach the same sort of non-locality and weird statistics by using Einstein-Rosen bridges. Um, and I think this is already quite cool. So that's kind of the point of the paper. Again, as I said, I don't want to go through all of it. I think it's readable. You just need to read like kind of one line at a time, and then you can learn a bit more about this ER equal EPR conjecture. You may find actually, just to remind you, so this is this paper. You may find some other papers on it that are nice but and readable, but some of them I found were not as readable as I wanted to, and this one seems to be the most readable. So basically, that's it. I hope at least I piqued a little bit your curiosity about ER equals EPR. Again, trying to draw connections where people are not expecting necessarily, and that if you've got any questions or comments, you let me know in the description. Otherwise, see you in the next video.